Hi, I hope that you are doing great. In this video I am going to solve the problems related to lecture 15, Factoring Polynomials Part 4. If you're following my YouTube channel, you probably know that there is a playlist on my YouTube channel called Advanced High School Algebra. This video is uploaded onto that playlist. In the descriptions below the video, you find 5 links. The first link gives you access to a PDF file containing the problems that I'm going to solve in this video. The second link is the link to the PDF file of these notes that right now you see on your displays, and I am moving it a little bit. You see, this is every questions that I'm going to solve is already in this file, and then I will write my solutions on these empty spaces that I have already provided in the notes. In this file, the solutions to the problems that I will present in this video are not included. I use iPad Pro together with Apple Pencil and GoodNotes 5 application to produce these videos. The content of the third link is exactly the same as the second one, except that this one is the GoodNotes file. I strongly recommend you to have one of these files available when watching the video. If you have access to a tablet with GoodNotes installed on it, then you can use the third link to download these lecture notes, these notes that you see here, directly onto your tablet, as if you yourself have created them in the first place. Otherwise, you can use the second link to download the PDF version of these notes and print them. I think having the notes in front of you while watching the video could be very helpful in active learning. Finally, the fourth and fifth links are links to a PDF and GoodNotes file accordingly of these lecture notes, but they contain all my solutions to the problems and all my explanations in written form that I will finish by the end of this video. At the end, I spent many hours enthusiastically to make these videos available for free. If you found the video somehow helpful and enjoyed watching it, I will be very happy if you could give me a thumb up. By subscribing to my channel, you will be immediately notified if I upload a video. Okay, now let us start. Okay, now, so let us start the first problem. Factorize the following polynomials on the set of integers. I have emphasized to do it on the set of integers, even though by default this is always meant to be the case. Okay, so here I have a polynomial. I want to factorize it, and I want to use the long division method. So first of all, I need to list the factors of minus 4 in front of me. So I will write factors of minus 4. What are they? Plus and minus 1, plus and minus 2, and finally plus and minus 4. Then I will start checking them one by one. And then I am very lucky because the first one will work, because if I put x equal to 1, then if I call this p of x, this polynomial, then p of 1 becomes equal to 1 plus 3 minus 4, which is indeed 0. So then it implies that this will imply that p of x is divisible by x minus 1. Yes? So then I do the long division. So I would write x to the 3 plus 3x squared minus 4, and then I divide this by x minus 1, and I do the long division. Okay, so the first term divided by this first term will give me x squared. I multiply it and write it here. So I multiply this x squared here, and I would write the terms here, and then I will change the signs and then add them. So it means that I am subtracting them. Yes. So if I multiply, this becomes x to the 2, x to the 3, minus x to the 2, yes, and then I will change the sign, so this becomes negative, this becomes positive, and then what I do, I add them. So when I add them, this term and that term are cancelled, and then I have 3x squared, positive x squared gives me 4x squared, and then I will bring minus 4 down, and then I will continue the process, yes. So what should I do? I need to divide the first term 4x squared by x, so I will get positive x, so I will write it here, positive 4x, and I will repeat that process. So I will multiply 4x there, it becomes 4x squared minus 4x, and then what I do, I change the sign positive to negative, and I negative to positive, yes. So then I will add them, so what I get is 0, and then I will have positive 4x minus 4, so these two terms actually cancelled. And I repeat the process, so I will have 4 here, I multiply it, it becomes 4x minus 4, I will change the signs negative, positive, and then I will have the remainder as I expected becomes 0 when I add. Yes, so this, as I expected, it is divisible, the remainder is 0, but I did this because I wanted to actually factorize the polynomial. So what can I write now? P of x is equal to the divisor multiplied by the quotient plus the remainder. So then what happens? It becomes x minus 1 multiplied by x to the 4 plus 4x plus 4. So this is the factorized form of my polynomial, but of course it is not fully factorized, and you can immediately see what will happen here. So this one is a quadratic rule, so I can write it as x minus 1, then I will have x plus 2 to the power of 2. Yes, so this I would call it the factorization of my polynomial. Yes. And of course, now that you have this long division in front of your eyes, you can use the breaking terms into different terms. Yes, so you see here, for example, you can immediately see that this 3x squared has been broken to minus x squared here and positive 4x squared here. So now that you have this long division in front of you, you can, if you want, to do it the other way around, but it was not easy from the beginning to guess this. Of course, for this problem it was not that hard to guess, but in principle it is not that easy to guess. So what I'm trying to say is that if you want, you can now do it in this way. Yes, so what can you do? Instead of 3x squared, which is this one, you can write minus x squared plus 4x squared. Yes, so it becomes x to the power of 3 minus x squared plus 4x squared minus 4. Then I can group these two together and these two together. Yes, so then what can I do? I can factor x squared out from the first two terms, and then I can factor 4 out from the last two terms, and then I can write x squared x minus 1. The next one is plus 4, and I can factorize it using the conjugate pattern x minus 1 x plus 1. Yes, and now you see that this actually emerges. This is a common factor, so I can pull it out. So then it becomes x minus 1. So what is left from the first one is x squared, and what is left from the second one is 4 times x plus 1. And then I multiply that 4 in, so it becomes x squared plus 4x plus 4. And then, as you see, I can just continue one more step and write x plus 2 to the 2, and I will get the same answer. Yes, I would say that of course this is easy here in this case to guess, but in general, realizing which terms are suitable for breaking some of the terms is not easy at all. Okay, so now let me draw a line here to make it simpler for us. Okay, so I can start solving the other one here. So we want to factorize this polynomial again. So that is our goal. We want to factorize this polynomial. And then we don't have any extra information about that. Hoping that this has an integer root, I will go and try to look at the factors of this constant term. Yes. So what I would write is that factors of 4 are again as before plus and minus 1, plus and minus 2, and finally plus and minus 4. So these are the factors. Of course, here I don't need to consider positive ones at all because all the signs that you see are positive, so there is no point to checking positive ones. So let us start with negative ones. So negative 1, I will check negative 1. So if you don't mind, let me call this one q of x this time, and I want to calculate them one by one. So q minus 1 is minus 1 plus 7 minus 10 plus 4. We are lucky. So the answer becomes 0. So what does it mean? It means that q of x is divisible by x minus the number that we got minus 1, which is x plus 1. So what we need to do, we need to divide this polynomial qx by x plus 1, and then definitely we will get the remainder equal to 0. Yes. Okay, so let me just do that. So I will have x to the 3 plus 7x squared plus 10x plus 4, and then I divide this by x plus 1. And let me change my color now. So the first term divided by the first term is actually x squared. I multiply it here and write it here, so it becomes x cubed plus x squared, but I am supposed to change the signs, and then I need to add them. So when I add them, the first term actually cancel this one, and then I have minus x squared plus 7x squared, which will give me 6x squared. Then I will bring 10x down and positive 4 as well. Okay, and the next step is to divide 6x squared by x, which gives me 6x, and then I multiply it, so it becomes 6x squared plus 6x. Then I will change the signs, so this becomes negative, this becomes negative, and then what can I do? I add them again. This term and that term are cancelled. Then I will get 4x plus 4. And finally, I know that this is positive 4. And if I multiply it by positive 4, it becomes 4x plus 4. And then I will change the signs, and then I will get 0. Yes, as expected. And now what I can do, I can write that q of x is equal to the divisor multiplied by the quotient plus the remainder. The remainder is 0, so it becomes just x plus 1 times x squared plus 6x plus 4. And then you know that this would be the final form. How should I know that? I cannot factorize this more on the set of integers, because do I have two numbers do I have integers whose product is 4, and as the sum is positive 6? We don't have it. And if you think that this would be hard, you can find the roots of this equation. The roots of this equation, it's not that hard. Using ABC formula, you see that the roots are involved with square roots. They are irrational actually. So this means that this is the end of the problem. Okay, and let me give you one more advice. So how could I now that I have this in front of my eyes, how could I solve this one by breaking the terms? And then you see that this is not easy. So let me make this smaller so then you can see it here. Now you see here I have 7x squared. Look, 7x squared is here. It has been written as positive x squared plus 6x squared. Okay, so let me write it down. So if you want to solve it using breaking the terms, then it becomes qx. X cubed is just x cubed, and instead of 7x squared, I put x squared plus 6x squared. Yes, how did I realize that? By looking at this term and this term. And then look here, I have a 10x. 10x appears here, and then you see that this is written as the positive 6x, positive 4x. So this will give me this, that I need to break this one as well to 6x plus x. Yes, it becomes 7x, plus 4x. Plus 4x, 10x, and then at the end I will have positive 4. So what you see here is exactly qx, but then using this I realize that I need to break 7x squared to the sum of x squared and 6x squared, and then 10x to a sum of 6x plus 4x, and these are probably the only ones that work. Okay, so you see that it was not easy at all. Now my goal is to make the factor of x plus 1 emerges, and that is now easy to see how I can take this one, because my intention is to make x plus 1 appears. Yes, and then immediately you can see I can factor 6x out between these two, and finally I can factor 4 from them. But it was not easy. I hope that you agree with me. It was not clear from the beginning that one can do that. So then I continue and I factor x squared out from the first two terms, so I will have x plus 1. I will factor 6x from the second group, it becomes x plus 1, and finally I factor 4 out, it becomes x plus 1, and now you immediately see that I can factor x plus 1 out, and it would be x squared plus 6x plus 4. Yes, and that is exactly the answer we got from this one. Okay, of course one of these is completely enough, you don't need to solve both of them, but I'm trying to say that if you really want to be able to find those terms, this is one way that you can do it using this long division method. Okay, now we go to the actually next problem. Okay, so let us go to the next problem now. We want to factorize this polynomial now on the set of integers. So let me call it as before. So let me call it p of x. So what we should do, again, we consider factors of this constant term, minus 6. So they are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. Yes. So if you check, I have already done that, none of them is actually a root of this polynomial. So if you calculate p plus or minus 1, if you calculate p plus minus 2, plus p plus minus 3, and finally p plus minus 6, none of them is equal to 0. So what we can conclude? We can conclude that p of x does not have any integer roots. But this statement on its own is not enough to conclude that we cannot factorize this polynomial on the set of integers. Because it might happen that my polynomial, we have this kind of examples in the previous lecture. If you have forgotten, you can go and review that. It might happen that I have a polynomial with integer coefficients. My polynomial doesn't have any integer root, but it is still possible to factorize that polynomial on the set of integers. Yes. So if I want to give you a quick example, so consider this polynomial 2x plus 1 multiplied by 3x plus 1. Yes. So it is clear that this polynomial doesn't have any integer roots, yes, because the roots are -1/2 and -1/3, but as you see, it is still factorizable over the set of integers because the numbers involved are all integers. Okay, so the fact that this polynomial doesn't have any integer roots, it's not enough to conclude that we cannot still factorize that. You see, this is a counterexample. But if we do not have any rational roots for the polynomial, then it is guaranteed that at least we cannot factorize it. We cannot factorize it at least on the set of integers. Okay? But let us check. Do you think that this polynomial has a rational root which is not in this list? No. The reason is that if you remember, we had a theorem on the previous session that if S over T is a rational number such that P of S of T is equal to 0, yes, then it means that the numerator S should be a factor of the constant term minus 6, so S should be a factor of minus 6, and the denominator T should be a factor of this number, this coefficient, which is 1. Should be a factor of 1. So this means that therefore T is plus or minus 1. And the factors of 6 are exactly these numbers. So S over T are the numbers in this list divided by plus or minus 1. So if I do that, I will not get any new number out of this. Yes, all the numbers would be exactly the same, and they are not roots of my equation. So it means that this polynomial doesn't have any integer roots. This polynomial doesn't have any rational roots either. So then it means that I cannot factorize this polynomial over the set of integers. Yes, so then we conclude that this polynomial cannot be factorized over the set of integers. Now let us go to the next problem. So let me draw some lines for the border. So here I can split this into two parts. Yes, yeah, good. Okay, now we want to factorize this polynomial. So this is I would say this is highly non-trivial because first of all the degree is 4 and then these numbers are fairly large. Okay, so again the strategy is as before. So what we do, we write the factors of minus 120. There are quite a lot of them. So it's plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 5, up to plus and minus until 120. Yes. Okay, let me call this one q of x. So let me call this q of x. And then let us calculate. So what is q of 1? If I calculate q of 1, it's 1 minus 4 minus 19 plus 106 minus 120. Yes, so you can immediately see that this number is not equal to 0. So what happens if I calculate q of minus 1? It becomes 1 positive 4 minus 19 minus 106 minus 120. Again, it's not equal to 0. Let me calculate q of 2. q of 2 is 16 minus 32 minus 4 times 19 is 76. Yes, and then I have 2 times 106 is 212, and then I have minus 120. Okay, so what is here? This is 92. It's minus 92. Yes, that is 0. Okay, so one possibility is that you immediately go and factorize this polynomial using the long division, because now we know that 2 is a root, so this polynomial is definitely divisible by x minus 2. But of course I did this way when I was doing the lecture, the main lecture. Let me do it in another way. Of course, if you do this, then your quotient would be a third degree polynomial. Again, you need to do the same trick for that third degree polynomial to be able to factorize that if possible. Okay, so let me so I'm not saying that this is wrong. Actually, I did this way when I was lecturing, but now I can do one more thing. So let us, for example, calculate the other one as well. For example, let us see what happens for q of 3. If I put 3, then it becomes 81 minus 108. So then it becomes minus 171, yes, and then I will have 318 minus 120. So then what you get, you see that this is also equal to 0. Yes. Okay. So let me stop here, because now I know that q2 is equal to 0. So this means that q of x is divisible by x minus 2. We realize that q of 3 is also 0. So we say that q of x is divisible by x minus 3 as well. Yes. Okay. Now I know that my polynomial qx is divisible by x minus 2, and it is also divisible by x minus 3. And one more thing, and x minus 2 and x minus 3 don't have any factor in common, except of course 1. Yes? So then this means that q of x, therefore q of x is divisible by the product. By the product of these two polynomials, x minus 2, x minus 3. But another name for this, using the common term identity, it is x squared minus 5x plus 6. So this means that my polynomial q of x is definitely divisible by x squared minus 5x plus 6. Okay, so instead of dividing q of x by x minus 2 to get a third degree polynomial and repeat the process, I was a little bit patient because I checked that I could find two roots, and then these factors are that doesn't have anything in common, doesn't have any factor in common except 1. So if a polynomial is divisible by x minus 2 and it is also divisible by x minus 3, definitely it is also divisible by the product, which is x squared minus 5x plus 6. So instead of dividing my polynomial by x minus 2 and x minus 3 individually, I will divide it by this x squared minus 5x plus this. Let me write this here, and then I will make it bigger. So let me write it here. So I will have x squared, x to the 4 minus 4x to the 3 minus 19x to the 2, and then I will have plus 106x minus 120. And by the way, I can move it a little bit to the left to have enough space. Okay. And then I can have this, and I have this. I can divide now by x squared minus 5x plus 6. Okay? Now I can make it bigger. Okay, so if I divide the first term by the first term, I will get an x squared here. I multiply it here, it becomes x to the 4 minus 5x to the 3 plus 6x to the 2. Then I will change the sign. This becomes negative, this becomes positive, this becomes negative. And then I add them together. So what I get is this one and this one are cancelled. This one and this one are cancelled. Positive 5x to the power of 3 minus 4x to the 3 becomes positive x to the 3. Negative 6x squared minus 19x squared is minus 25x squared. And then I have to bring the rest, 106x and minus 120. And I repeat my process. So what should I do? I divide x3 by x squared, it will give me x, and I multiply it. So it becomes x to the 3 minus 5x to the 2, and then I will have positive 6x. Yes, then I will change my signs, so this becomes negative, positive, negative, and then add them. When I add them, this and that are gone, so I get positive 5x squared minus 25x squared, which gives me a minus 20x squared, and then I will get positive 100x minus 120. And then you immediately see that the next term would be minus 20, and if I multiply it, it becomes negative 20x squared, positive 100x, and negative 120. Now again, as before, I change the sign, so it becomes positive, negative, and positive. And then when I add them, all of them vanish. Yes, this and that are gone, this one and that one are also gone, this is also gone. So as I expected, I get 0 at the end. But now what can I write? This is my polynomial. I called it qx. I am supposed to factorize this. You see, I called it qx. So I would write that my polynomial q of x is equal to the divisor multiplied by the quotient plus the remainder. So what I get is that qx is x squared minus 5x plus 6 multiplied by x squared plus x minus 20. Yes, and I think you have enough experience that you immediately see that I can continue and factorize these two polynomials. Yes, so I can write two pairs of brackets, put x here and there, and another two pairs of brackets for the next term, and I put x here and x there. So here I ask myself, I need two numbers whose sum is minus 5 and the product is positive 6, so it's clear that one of them is minus 2, the other one is minus 3. And then here I need two numbers whose sum is positive 1 and the product is negative 20. And then it becomes positive 5 and negative 4. So you see that this is the complete factorization of your polynomial. Okay, but of course, if you want to do it using the breaking terms, it is quite challenging if you don't have this in front of your eyes. But now that you have this in front of our eyes, probably we can do that. Let us just write it for you. So here you see that I have x to the 4, so let me write qx is equal to x to the 4. But let us see the next term. What is the next term? The next term is minus 4x3. But you see, it is minus 5x3 plus x3. So I need to break minus 4x3 to minus 5x3 plus x3. So I will do that. So it becomes minus 5x3 plus x3. Yes. And now let us go to the next term, minus 19x squared. Minus 19x squared is positive 6x squared minus 25x squared. But minus 25x squared itself is minus 5x squared minus 20x squared. So I need to break minus 19x squared in 3 terms, which was not easy to predict before seeing this actually. So let me just do that. So instead of minus 19x squared, I would write positive 6x squared minus 25x squared, but minus 25x squared itself is minus 5x squared minus 20x squared. So it's minus 5x squared minus 20x squared. Yes. Okay, and then the next term, 106x, appears here. It can be written as plus 6x plus 100x. So it becomes plus 6x plus 100x. And then finally I have minus 120. So if you don't mind, let me move this a little bit to the left so that I have enough space. 100x, 100x, minus 120. Okay, and if you insist to continue in this way, so you see it was really hard to see that this term should be written in this form, and this term should be split into three terms in this form. Yes, and then this next term should be split into two terms in this form. And now your goal, if you want to continue using this method, your goal should be to make somehow x squared minus 5x plus 6 appear here. So what can I do? For example, I can take this one and this one. My goal is to factor x squared out, so I will have this one. So let me just do it not to get confused. So I will get x squared out, so x squared minus 5x plus 6 is left. Okay. And the next one, I can take these two, these three, this one. My goal is to factor x out, and this one, and then this one. I can factor x out, yes. So it becomes plus x, and I will have again x squared minus 5x plus 6. And now what are left, I can take them together. So this one, and this one, and this one. I can factor minus 20 out. Yes, so it becomes minus 20. What is left from the first one is x squared minus 5x plus 6. And then you see that this is a common factor appears here. So you can write x squared minus 5x plus 6, and then you have x squared plus x minus 20. And I don't continue because this is exactly what you see here and know how to continue. But remember, this was not easy at all, even for the people who are expert here. Finding these terms are not easy. But when you have it in front of your eyes, you can know how to break the terms. Okay? Okay, so I think that is good. We go now to the next problem. Okay, we want to factorize this polynomial now. So it's a polynomial with integer coefficients, so we just follow the same rules. So let me just call it again p of x for simplicity of calling it. So the factors, I need to consider the factors of 64, which are plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8, and then you can continue up to plus and minus 64 finally. Okay, and then let us check the numbers one by one. Yes, for 1 and minus 1, it's not an answer, it's easy to see. But let us check p of 2 now. So p of 2 is equal to 16 plus 32 minus 48 minus 64 plus 64. Yes, so this is gone. Yeah, that's 0. So this implies that p of x is divisible by x minus 2. Yes. And of course, I can start dividing this polynomial p of x by x minus 2, but then of course I will get my quotient to be a third degree polynomial, and then I need to do the same process once more. But then I can see that minus 4 might be an answer here, because if I put minus 4 here, it becomes 4 to the 4, and then it becomes minus 4 to the 4. So let us check that one as well. If it doesn't work, then I will go and divide. So p of minus 4 is minus 4 to the 4 plus 4 times minus 4 to the 3 minus 12 times 16 plus 128, and then I have plus 64. But then you can see that this number and this number are opposite. Yes, because minus 4 to the 4 is positive 4 to the 4, but this becomes negative 4 to the 4, so they are cancelled, and this becomes 192, and this becomes minus 192. So that is also correct. So this is also 0, so this implies that p of x is divisible by x minus minus 4, which is x plus 4. Yes. Okay, now what we know that the only common factor for x minus 2 and x plus 2 is 1. We know that p of x is divisible by both x minus 2 and x sorry, this is not plus 2, this is plus 4. Okay, and then we know that px is divisible by both x minus 2 and x plus 4. This implies that p of x is divisible by the product by x minus 2 times x plus 4. Yes, but this is equal to x to the 2 plus 2x minus 8. So we realize that my polynomial px is divisible by that expression. So I can now set up this division. So what I can do is that, so let me make it a little bit smaller to see it. So it's x to the 4, let me write from the corner. So x to the 4 plus 4x to the 3 minus 12x squared minus 32x plus 64. Then I divide this by the expression that I got right now, which is x squared plus 2x minus 8. Yes, and I do the division. So x to the 4 divided by x to the 2 gives me x to the 2. I multiplied everything, so it becomes x4 plus 2x to the 3 minus 8x to the 2. Then I will change the signs. This becomes negative, negative, this becomes positive. And then I add them. This one and that one are gone. This becomes positive 2x to the 3. This becomes 2x to the 3. And then it becomes minus 4x squared. When I add this one with positive sign and this one, it becomes minus 4x squared. Then I will bring down minus 32x plus 64. And I do the process once more. So what happens? I will get if I divide 2x to the 3 by x squared, I will get 2x. And when I multiply it and write it here, it becomes 4x squared minus 16x. Yes, I will change the signs so it becomes negative, negative. This one becomes positive. Yes, and then I add them. So this one and that one are gone. Now it becomes minus 8x squared and minus 16x plus 64. And when I divide, it becomes minus 8. So I put minus 8 here and then I multiply. So it becomes minus 8x to the 2 minus 16x plus 64. Then I will change the signs and then I add them. It becomes 0. Yes. So it means that I actually succeeded in doing the long division, and then this one, which is my polynomial, is the product of the divisor by the quotient plus this one. So let me just write it here. So my p of x is now equal to x squared plus 2x minus 8 multiplied by x squared plus 2x minus 8 again. Yes, so that was interesting. Both of them are actually the same. Yes, so I can simplify that to x squared plus 2x minus 8 to the 2. But it might happen that I can still factorize this quadratic polynomial. Yes. Is it possible to find two numbers whose sum is positive 2 and the product is negative 8? The answer is yes, and that is easy. So I open two pairs of brackets, I put x here and x here, and because of this power 2 I can write it here in this form. Yes, so I need two numbers whose sum is positive 2 and the product is negative 8. So one of them is positive 4, the other one is negative 2. But I prefer to write it in this way, so I would write x plus 4 to the 2 times x minus 2 to the 2. So that would be the final form of my factorization. Yes. Okay, and then I told you that if you want to use breaking terms technique, then it might be a little bit hard here, but when you have this long division in front of you, you can probably do it simply. So what we need to do, we need to break the terms, yes? So I would write that my p of x is equal to, so look here, 4x to the power of 3 should be broken, but it is clear to what, yes? 2x3, 2x3. So what I write, I would write, I would write x to the 4 plus 2x3 plus 2x3. Yes. And then I go to minus 12x squared, which is the next term, which is minus 8x squared minus 4x squared. Yes. So it becomes minus 8. But minus 4x squared is minus 8x squared plus 4x squared again. So I would write it as minus 8x squared. Instead of minus 4x squared, I would write 4x squared minus 8x squared. Yes, so you see it was very strange decomposition. Yes, minus 8 is minus 16 plus 4 is minus 12, exactly as before. And now if you go to minus 32x, you have minus 32x here, which is minus 16 minus 16. So it's minus 16x minus 16x. And then finally you have plus 64. Okay, now my goal is to make this divisor appears here by grouping them. So let me make it bigger here for you. So I will take this x to the 4 and then I multiply it. So yeah, I will take this one and I will take this one together. And then I will take this one and this one and this one together, and then the rest of them together. Yes. So then, for example, I factor x to the 2 out from the first group, so it becomes x squared plus 2x minus 8. From the second group, I will factor 2x out, so x squared plus 2x, and minus 8 is left. And from the last one, I factor minus 8 out, x squared plus 2x minus 8 is left. And as you see, now I have a common factor, so I can factor it out, so it becomes x squared plus 2x minus 8. Then I will have x squared from the first one, 2x from the second one, and minus 8 from the last one, and you get as the expression as you got before. And of course you can continue as you did before. Okay, so yeah, I go to the next page. Now for the next problem, this was the problem from the previous page, so I already solved that. So let me solve this one. So let me call this one q of x. Yes, if I want to factorize that, what should I do? I need to consider the possibility that might be that this polynomial has integer roots, or at least one integer root. But then I need to check the factors of 2. The factors of 2 are plus and minus 1, plus and minus 2. So I need to check them to find the possible root. I will check, for example, q of 1, but then it becomes 6 minus 7 plus 8 minus 7 plus 2, so which is not 0. Yes, I check q minus 1. It becomes 6 plus 7 plus 8 plus 7 plus 2, which is definitely not 0. I check q of 2. What is q of 2? It is 16 times 6 is 96, minus 8 times 7, 56. And then I will have 32. It's 72 for the time being. And then I have minus 14 plus 2, definitely not 0. And finally, I will check q of minus 2, which is again 96 plus 56. And then I will have plus 32 plus 14 plus 2, not 0. Okay, so it means that q of x does not have any integer roots. Yes? But it might happen that still this polynomial has rational roots. So if s over t is a rational root, if s over t is a rational root, then what does it mean? It means qs of t is 0. Then you need to know that from the previous theorem on the previous session is that s is a factor of 2. So this means that s is plus or minus 1 plus or minus 2, and t is a factor of this number 6. Yes, so this means that t is plus or minus 1 plus or minus 2 plus or minus 3 and finally plus. Okay, now so if this is the case, then I need to check s over t. Yes, so what happens for s over t? So s have these possible numbers and t are these numbers. So okay, so if I divide s by this t, I will not get something new. I will get either plus or minus 1, which I have already checked here. Yes, so the new numbers that I get, I will write the new numbers in my list. The new numbers are this situation, plus or minus 1 divided by plus or minus 2, so it becomes plus or minus a half. This is something new. And then we have this one divided by this, we have this one divided by this, so we get 4 more, plus or minus a third, plus or minus 1 over 6. And then we go to the next one. If I divide this by this, I will get plus or minus 2, but I have already checked them here. If I divide this by this, I will get plus or minus 1, which I have already checked that one. So I have to divide this by this. This is also new. And then finally, if I divide this one by that one, it becomes plus or minus a third that I have already in my list. So then I have 8 more numbers to check. If none of them is a root, then I will give up and I will say that this is not possible to factorize this polynomial over the set of integers. But if one of these numbers is a root, there is a chance that still I can factorize this on this. I definitely can factorize it on the set of rational numbers, but there is also a chance that I can factorize it over the set of integers as well. Yes. So for example, let us check these numbers one by one now. Okay, so now let me make this a little bit smaller so that I can see it here. So let us calculate q of 1 over 2. So then what happens? It becomes 6 over 16 and then minus 7 over 8, and then I will have 8 over 4 minus 7 over 2, and then I have 2. So let us simplify that. So this becomes 3 over 8. It's minus 4 over 8. It's minus a half. Minus a half and minus 7 over 2 is minus 8 over 2, which is minus 4. Minus 4 plus 2 is minus 2. and this is plus 2. It's 0. Yes? Yeah, we got it. So q of 1 over 2 is 0. So what does it mean? It means that q of x is divisible by x minus a half. Yes? So because the fraction numbers are a little bit harder to calculate, so let us just divide right now to see how it goes. Okay, so let me make it smaller and divide it to two parts. Yes, so here, and then I can go here and then divide my polynomial by x minus a half. So let me just do it here. So I have 6x to the 4, make it bigger. Yes, I have 6x to the 4. I have minus 7x to the 3 plus 8x to the 2 minus 7x plus 2. Then I divide this by x minus a half. Yes, okay. So the first term divided by the first term, it gives me 6x to the 3. So I multiply it there, it becomes it becomes 6x to the 4, and the other one becomes negative 3x to the 3. Okay, I will change the signs, so this becomes negative, this becomes positive, and then what I do, I add them. When I add them, this one and that one are gone. What I get is minus 4x to the 3, and I will bring down the rest of it. And then I do the division once more, so it's minus 4x to the power of 2. When I multiply it, it becomes minus 4x to the 3, and then it becomes positive 2x to the 2. I will change the signs positive, negative, then I will add them. This one and that one are gone. What I get is 6x squared minus 7x plus 2. I divide once more, so it becomes 6x. When I multiply it, it becomes 6x squared, and then I have minus 3x. I will change the signs, yes, and then I will add them. When I add them, this is gone, and I will get minus 4x plus 2. And what I do, it's minus 4 here, it becomes minus 4x, and then I will get plus 2. I will change the signs, and then I will add them. Yes, when I add them, as I expected, I will get 0. Okay, so what can I do now? I can go and write the divisor multiplied by the quotient gives me the remainder. Okay, so far what I have done, you see, 6x to the 4. So let me write qx for simplicity. So qx is equal to x minus a half multiplied by 6x to the 3 minus 4x to the 2 plus 6x minus 4. Yes, you might think that I was not able to factorize it over the set of integers because 1/2 is not an integer, but look, here I can factor 2 out of it. Yes, so I can factor this 2 out. So let me write it with different color here. So this becomes 3x to the 3 minus 2x to the 2 plus 3x minus 2. Yes, and then what happens, this 2 that I brought this out, I multiply it here, so then it becomes 2x minus 1 multiplied by 3x to the 3 minus 2x squared plus 3x minus 2. Okay, so far I was able to factorize my polynomial over the set of integers, because now you see that all these numbers involved are integers. Okay, now it might happen that still we can factorize this polynomial. Okay, this polynomial doesn't have any integer roots, because if this has an integer root, that integer root would also be the integer root for q of x, but we realized here that q of x doesn't have any integer roots. So the only hope that we have for this is to have a rational root and then it is of this character that I can factor something out, and I can get rid of the fractions at the end if possible. Okay, so it means that we don't need to look for integer roots here. What I need to consider is only the rational roots, and again as before, so let me call this one, let us give it a new name, so let me call it kx. So if k of, again, s and t is equal to 0, if s over t is a rational number, then what you can see is that s is a factor of -2 and t is a factor of 3. So this means that for s I have plus and minus 1 plus and minus 2, and for t I have plus and minus 1 plus and minus 3. Okay, but s, if you take s this one and this will give you an integer, so I don't want it. I know that there is no integer root, so the possibilities of s over t are only plus and minus a third, and then plus and minus 2/3. Okay, but I have already checked that this will be the answer. So let us calculate k at a minus. Let us calculate k at 2/3. Then if you calculate this one, you will get 0. Okay, so you can check it yourself. And then this means that k of x is divisible by x minus 2/3. Yes. So now what I do the long division for this k of x. Yes, so I divide this by x minus 2/3, and then I can change my color now here. So the first term, it becomes 3x to the 2. When I multiply it, it becomes 3x to the 3, and then it becomes minus 2x squared. Now what I do, I change the signs, and then what I do, I add them. This one and this one are cancelled, and this one also cancelled. So I will get 3x minus 2, and I do the division once more, so it becomes plus 3, and it becomes 3x minus 2. When I change the signs, it becomes negative positive, and then I add them. This one and that one are gone, this one and this one is also gone, so I will get 0. So what does it mean? It means that the k of x, so let me write it here, k of x, I can clean this. So k of x is equal to x minus 2/3, which is my divisor now, multiplied by my quotient, which is 3x squared plus 3. Again, you see that the same scenario, you can factor a 3 out from here, it becomes x squared plus 1, and then you can multiply this 3 here. So then it becomes 3x minus 2, x squared plus 1. Yes, and the good point is that now all these numbers involved are integers, and if you plug this back here in this equation, you will finally find your qx in a factorized form. So it is 2x minus 1, and then it becomes 3x minus 2 multiplied by x squared plus 1. And you know that x squared plus 1 cannot be factorized over the set of integers. You need complex numbers to be able to factorize this. Okay, so now let us go to the next problem. Find all the real roots of the following equation. So here the goal is, of course, the primary goal is not to factorize the polynomial, but we are supposed to solve a 4th degree polynomial equation. Okay, so it means that we somehow have to factorize this polynomial into factors with lower degrees, so that we know and then use the zero product rule to put each one of those factors equal to 0, and those factors have smaller degrees, and we know how to deal with them. So that is the idea behind this. So even though they haven't directly asked you to factorize the polynomial, but if you want to solve this equation, you yourself have to understand that you need to factorize the polynomial in the beginning. Okay, so let me, as usual, call the polynomial itself only p of x, and try to factorize this as we learned so far. Okay, so hoping that this polynomial has an integer root, so let us see if I can find them. So I need to look at the factors of this constant term for the, so factors are 1. So you can, the factors of 1 are plus and minus 1. So let us calculate P1. So if I calculate P1, it is 2 minus 5 minus 1 plus 3 plus 1. Yes. Is it 0? Yes, this is indeed 0. So this means that P of x is divisible by x minus 1. If I check the other one, of course here at this point I can start dividing this polynomial by x minus 1 using the long division, but of course you know that this is the first degree, this is the fourth degree. If I divide them, the quotient would be of third degree, and if I want to solve that third degree equation, I have to be able to factorize it even more. That's completely acceptable. But let us try to see if I can find other roots here at this stage. Okay, so p of minus 1 is 2 plus 5 minus 1 minus 3 plus 1. Yeah, of course this is not equal to 0. So it means that I have only one integer root for p of x, and that is x equal to 1. But it might happen that still I might have rational roots, fraction roots, yes. So if s of t, if s over t is going to be a rational root for this polynomial, meaning that p of s of t is equal to 0, so then you know that the numerator s should be a factor of 1, so it means that there are two options for s, plus or minus 1, and the denominator should be a factor of this term too, so it means that t is also plus and minus 2. So then this implies that s over t can be only two different numbers, plus or minus 1 over 2, nothing more. So let us check at least one of them. Let us see if they are solutions. So p of 1/2, if I check that one, so it becomes 2 over 16 minus 5 over 8, then I have minus 1 over 4 plus 3 over 2 plus 1. So let us see how it goes. So this is 1 over 8. 1 over 8 minus 5 over 8 is minus 4 over 8, which is minus 1/2, and minus 1/2, but 3/2 becomes 1. So yeah, it is not 0. Okay, so let me check p of minus 1/2. Then this becomes again 2 over 16, but the next one becomes positive 5 over 8 minus 1 over 4 minus 3 over 2 and then plus 1. Let us calculate this one as well. So this is 1 over 8. 1 over 8 plus 5 over 8 is 6 over 8, which is 3 over 4. 3 over 4 minus 1 over 4 is 2 over 4, which is 1 over 2. 1 over 2 minus 3 over 2 is minus 2 over 2, which is minus 1. Minus 1 plus 1 is indeed 0. So this means that p of x is divisible by x minus 1/2, which is x plus 1/2. Yes. So what we have so far, we have that p of x is divisible by x minus 1. We know that p of x is divisible by x plus 1/2. So it means that, and then because the only common factor between x minus 1 and x plus 1/2 is 1, it means that p of x is also divisible by the product. Yes. So P of x is divisible by the product x minus a half times x plus a half. Yes, and then you can use the common term identity, the common term to the two, the sum of these two numbers, which is minus a half, multiplied by the common term, and then the product of these two terms. So coincidentally, both of them here becomes minus a half. So it means that my polynomial p of x is now divisible by this polynomial, so I can start the long division process. So let me start from here. So I have 2x to the 4 minus 5x to the 3 minus x squared plus 3x plus 1, and then I divide this by this polynomial, x squared minus a half x minus a half. Yes. So let me open a little bit of space here. Yeah, good. Okay, now let us start the process of division. So the first term divided by first term gives me 2x squared. Then I multiply it, it becomes 2x to the 4 minus x to the 3 minus x to the 2. Then I will change the signs. So this becomes negative, this becomes positive, this becomes positive, and then I add them. When I add them, this term and that term are cancelled. This term and that term was also cancelled. So this one, I have positive x3 minus 5x3, so it will give me minus 4x to the 3. Oh, sorry. 4x to the 3. And then I will bring 3x and 1 down, yes. Okay, now I continue once more. So minus 4x3 divided by x2, it gives me minus 4x, and I multiply it, so it becomes minus 4x3 positive x squared positive 2 positive 2x squared positive 2x squared positive 2x. Okay, what I need to do, I need to change the signs now. So this becomes negative, this becomes negative. Sorry, I made a mistake here. So this was positive, this was negative from the beginning. Yes, you see minus 4x times this, it becomes minus 4x cubed. And if I multiply it here, it becomes positive 2x squared and positive 2x. Yes, everything is right now. So I will change the sign. So this becomes positive, negative, negative. And then if I add them, then the first term and the first term are cancelled. Then I bring minus 2x squared first. And then you see that minus 2x and positive 3x will be positive x. And then I will have positive 1. And if I do the division once more, I will get minus 2. So let me change the color. So minus 2, it becomes minus 2x squared plus x plus 1. And if I change the signs, positive, negative, then negative, and add them, this time everything becomes 0. So this would be my divisor and this is my quotient. So what can I write? I can write that p of x is the product of these two. X squared minus a half x minus a half, and then I have 2x squared minus 4x minus 2. Of course, at this point we don't need to continue more because the goal of this problem is not factorizing. The goal is to solve this equation, and then I have been able to factorize this polynomial up to this point, which is a product of two quadratic expressions. So I can put this equal to 0, and then using the zero product rule, I would say that either this one is 0, which is easy to solve using ABC formula, or this one is equal to 0, which is also easy to solve. But of course you see that this problem is involved with fractions, and if possible let us avoid from fractions, and in this case it is indeed possible. Yes, so what can I do? I can factor a 2 out from here. I can write it as x squared minus 2x minus 1. then I can multiply this 2 here to get rid of these fractions. So a better way of writing p of x would be 2x squared minus x minus 1, and then I will have x squared minus 2x minus 1. Of course, if the problem is to factorize the polynomial, you might think that we can continue for them, but I would say that let us not to do that, because our goal is not fully factorize. Our goal is to find the roots, and we already know the ABC formula, so we don't need to waste the time to spend more time to find the better factorization of p of x. And of course I can do it at the end if you want to see how it goes. Okay, so what I do, my problem is to solve p of x equal to 0. So if I put p of x equal to 0, this means either this one is 0, so this implies that 2x squared minus x minus 1 is 0, or x squared minus 2x minus 1 is equal to 0. Okay, so let me call this one equation number 1, and let me call this one equation number 2. Let us solve them. So number 1, I have 2x squared minus x minus a half equal to 0. So what I get using ABC formula, this is 1 plus and minus 1 plus 8 divided by 4, yes? And then it becomes 1 plus and minus 3 divided by 4. So I get two answers. One of them is 4 divided by 4, which is 1. The other answer is 1 minus 3 minus 2 divided by 4 minus a half. So I got two roots here. And then number 2, x squared minus 2x minus 1 equals to 0. So what I can do, I can use ABC formula again. Plus 4 divided by 2. So this becomes 2 plus and minus square root of 8 can be written as 2 square root of 2 divided by 2. So if I factor 2 out and divide, this becomes 1 plus and minus square root of 2. So there are two more roots, 1 plus square root of 2, 1 minus square root of 2. So in total, this equation has 4 real roots. All of them are possible, yes, because we are supposed to solve the equation over the set of real numbers. And all these numbers that we get here, 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 and here, all of them are real numbers. So this equation is solved. But let us go back to the question. This is the complete solution of this problem. The goal was to solve the equation, not fully factorize. But if you want, you can also do full factorization if you like to see. Now you know that this one cannot be factorized over the set of integers, because you see that the roots are real numbers, not integers. I am using this formula, if you remember from some previous lecture, that this can be factorized into this form, where x1 and x2 are the roots. So of course I can factorize this again using this formula, but because the roots are real numbers, this cannot be factorized over the set of integers. Okay, so but this one might be, because one of the roots is integer and the other root is rational. So we might have the chance that this can be factorized. So let us check that one. So 2x squared minus x minus 1, according to this formula, is a in this case is 2, times x minus the first root times x minus the second root, which becomes positive 1/2. Then of course you see that I can use this 2 and multiply it here to get rid of this fraction. So then it becomes x minus 1 times 2x plus 1. Yeah, so that's the factorization of my polynomial here. So if you are interested, which is not of course the part of the problem, if you are interested to fully factorize your polynomial over the set of integers, I would say that this would be your answer. It would be x minus 1, 2x plus 1, and then x squared minus 2x minus 1. Yes, so that would be the full factorized form of your polynomial. But as I told you, that this is not needed in this problem. Of course, if you do it, that's no problem. Then if you put this equal to 0, then you would say that I have three numbers equal to 0. So either this one is equal to 0 will give you this root, or this one is equal to 0 will give you this root, and again this one equal to 0 will give you two other ones. That's also possible, but it was not necessary for this problem. Okay, now we go to the next problem. Factorize the following polynomial. The reason that I called it probably challenging a little bit, because it's not a very standard, I'm not saying this is hard, but not very standard one. So you need to be creative and try to find a way out of it. First of all, what I see that in this form I don't have any common factor to pull out. So the only thing that I can do is probably to expand it. So I would multiply everything inside the bracket. So the first will give me a squared b plus ab squared. The next one will give me b squared c plus bc squared. And the next one c squared a plus ca squared. And let me break this term into two abcs, abc plus abc. Okay, now we need to do some grouping in a way that we can see a common factor emerges. So let me take these two back again. My goal is to let me factor this AB out. So what is AB? If I take AB out, then A plus B is left. Now my goal is to make A plus B emerges from all other groups so that I can factor A plus B out. That's my strategy now. Okay, so what can I do? For example, I can take one of these ABCs and then B squared C here. Let us take these two. Yes, and take BC out. Let us just do it step by step. So I take BC out. From this one, A is left. From this one, B is left. So that is good. So far so good, because A plus B appears. Yes. Now I go to the next term. I will take one of these left ABCs here again with, I would say A squared C, for example. Yes. So what can I do? I can factor AC out this time. So AC is out. From this one, A is left, and from this one, B is left. Good, because my goal is to have A plus B. So what are left? So hopefully this also, yes, this also works. Yes. So if I take these together, yes, and then I factor C squared out, what I get is A plus B again. So this is very good now. You see, I have a common factor of A plus B. I can pull it out. Then from the first one, AB is left. From the second one, BC is left. From the next one, AC. And finally, C squared. Of course, this is already in factorized form, but it still might be that I can go further. And this is easy to detect, yes. If I take these two together and these two together, it will work, yes. It becomes A plus B, and then I factor B out from the first group, so A plus C is left, and I will factor C from the second group. Again, A plus C is left. I factored C out from these two. This is the answer. I factored B out from this group. This is the answer. This is good. Why? Because now A plus C is in common. So I can write A plus B, and I can pull A plus C out. B plus C is left. When I pull A plus C out, B is left from here, C is left from here. And that's the end of the problem. Okay? So you see, it was not hard, but might be you need to have some experience to be able to solve these problems. So the next one is more interesting. This one. Again, the same idea, yes? So if you want to factorize this, again, let us, by the experience that we got, so let us keep this one intact. I don't expand this. My goal is to make B minus A appear somehow, but let me expand these two, okay? I got this experience exactly from the previous problem. So this would be b minus a, and let me multiply. The first one becomes b to the 2 c to the 3 minus b to the 3 c to the 2. The next one would be c to the 2 a to the 3 minus c to the 3 a to the 2. Okay, don't forget, the goal is to make this combination somehow. Okay, so if that's the case, I have some guide now. So if I take this one with that one and pull out C3, of course I will not have b minus a, but I will have b squared minus a squared, but you can use the conjugate pattern. And then it's inevitable. If this is going to work, this should be the grouping. So let us continue now. So then it becomes a squared, b minus a. Between those two in this group, here and here, I can factor c cubed out. The first one is left b squared minus a squared. So far so good, yes? And then between these two, I can factor c squared out. Then I will have a3 minus b3. So that I will call it a wrong sign in the code actually, because b should come first and then a second. So it motivates me to factor minus c squared out. Then I will have positive b cubed minus a cubed. At first glance, you might think that this is not successful because I don't have any common factor emerging now. Yes. But you know what to do, hopefully. So this becomes a squared. You have a lot of experience of factorizing polynomials now. So b squared minus a squared is a conjugate pattern. So it becomes b minus a, b plus a. So good. You see now I have my b minus a that I need. And then this is the difference of two complete cubes, and you have the identity. So this is the cubic root of the first one minus the cubic root of the second one multiplied by the second one squared, the product with the opposite sign, and then the second one to the power of 2. So at least we were able to factorize this to some stage. B minus a is a common factor to all of them. So I will factor this out. So it becomes b minus a, and what is left is a squared b squared plus b minus a is left out, so c cubed and b plus a are left, so 3 to the 3 b plus a, and then here b minus a is pulled out, so minus c squared and this term are left, so it's minus c squared b squared plus ba plus a squared. Yes. And let me multiply it, because it might happen that you can factorize this a little bit more. So it becomes b minus a. I would write a squared b squared. I multiply c cubed in, so it becomes c to the 3b plus c to the 3a minus, I will multiply the other one as well. Yes. So at least you see this is in factorized form. But it might happen that we still continue. We might be able to still continue with that. Okay, so let us see what can we do. So you need to do some trial and error probably. For example, if I take this one with that one, I can pull b squared out. So what is left? A squared minus c squared will appear. So let me write. If I take b squared out, then a squared minus c squared is left. So my goal should be to make a squared minus c squared, or any combination of differences of powers of a appear. Powers of a and c appear, yes? So how can I do that then? So what can I do? For example, I can take this one with this one. Yes, that's also good, because if I factor ca out, only if powers of a and c will be involved. C squared out. Let me see, c squared a. Yes, that's correct. And then if this grouping is going to work, there is only one choice left for me, and take these two. Let us see if it works. So then it becomes b minus a. Okay, so what should I do? Between this one and this one, I can factor b squared out. So then it is a squared minus c squared. Between this one and this one, I can factor c squared and a out, but then it becomes c minus a. I want to have a minus c, so I will factor minus c squared a out. Then from this one, only a is left with positive sign, and from this one, c is left. Yes, let us double check. Minus c squared a multiplied by a becomes minus c squared a squared, which is correct. This one multiplied by that one, it becomes positive c cubed a, which is exactly this one. And then there is no other choice left. Hopefully if it works, then I will take this one and this one, and I can factor c squared b out. Again, for the same reason, I factor minus c squared b out. So if I factor minus c squared b out, from the second one a is left, and from the first one minus c is left. If you want to double check, multiply this back here, it becomes minus a c squared b minus a c squared b, and positive c cubed b, positive c cubed b. Okay, but still I don't have the common factor. The reason this is that this is a squared minus b squared, c squared, but then you know what to do. So you factor this one with the conjugate pattern, then the factor that you need emerges. Yes, now you can pull a minus c out from all of them, so this becomes b minus a minus c, and b squared times a plus c is left from the first one, minus c squared a minus c squared b. And still we have a chance, might have a chance to factorize this even more, so let me multiply that. So this becomes b minus a minus c, and if I multiply that, it becomes b squared a plus b squared c minus c squared a minus c squared b. So how can we factorize now? Okay, so we can take this one, we can take this one with that one and these two together, yes? So if I continue, this becomes b minus a minus c. Between the first group, I can factor a out, then b squared minus c squared appears. And between the other groups, I can factor a bc out, then b minus c appears. Again, I can do this. I can write b minus a minus c. I can factor this using the conjugate rule. Yes, and then again you see it was a little bit challenging. Yes, we have to do it a number of times. So b minus c, I can pull it out. So this becomes b minus a minus c, b minus c, and a times b plus c plus bc is left. So I don't think we can factorize it more, yes. So we just write it as it is. And I multiply it. It becomes ab plus ac plus bc. It's finished. But usually I prefer to write them in order. So instead of b minus a, I would write a minus b. The second term I will keep it as before. So I pull a minus sign out here and multiply this minus sign here. So it becomes c minus a. This is the way that you usually write when you have cyclic permutations for the variables. And then the next one I would prefer to write ab plus bc plus ca. It doesn't matter, you can end up on the previous line. So that is the full factorization of this polynomial. Yeah, it was a little bit lengthy actually, 1 page. Okay, but if you get some experience, you can do the other problems yourself. Okay, so let us go to the last problem of this problem sheet, and that is also this problem. Here we are supposed to factorize that. Yeah, first of all, let me mention, don't think that this is in factorized form. Yes, of course, this is a product. This part is a product. but then it is added from this sum number. So I have a product, I don't know, of 4 terms, and then I have plus 1. So in total, it is not in the factorized form. So let us see how we can go. What I found for this problem, you can take, I want to expand, but not I don't want to blindly expand this expression. I want to have a strategy using the common term identity. Yes, I want to because here I have 4 numbers that are supposed to be multiplied. It doesn't matter how I multiply and get the result and multiply the result to the next one. So I would prefer to multiply these two together and these two together. You will see that the reason is that, first of all, in each of these multiplications, I can use the common term identity, and then after multiplying it in this order, the new product will make a new common term identity. Let us see. So what I'm trying to say is that let us take this one and this one to multiply together, and then let us take this one and this one to multiply them together. Yes, so then it becomes equal to, for multiplying this one and this one, I use the common term identity. So the answer is the common term, which is x to the 2, the sum of these two numbers, which is 5, multiplied by the common term, and then finally the product of these two numbers, which becomes 4. I will do the same thing for the middle one, so this becomes the common term to the 2, the sum of the other terms, which is 5 again, multiplied by the common term, and then plus the product of those two numbers, which is 6, and then you see that you have a 1 at the end. But now, why this is good, why this was better, because now you see that there is a common term emerges again. So I can give the role of the common term here, and if I want to multiply them, I would say that this is the common term to the 2, yes, plus I need to add these two uncommon numbers, which becomes 10, and then multiplied by the common term, which is this one, and then I multiply these two terms together, it becomes 24, and then you see that I have a 1 at the end, so it becomes 1. Then what happens? It becomes x squared plus 5x to the power of 2, and then you have 10x squared plus 5x, and then you have 25. Yes? And I hope that you remember what we did for these kinds of polynomials in some sessions before. It's a quadratic pattern. It's not a trinomial, but it is written in term as if it's a trinomial. Yes, it is the sum of 3 terms. And the good point is that 2 of them are complete squares. So I get suspicious that it might be a quadratic rule involved. How should I check that? I go to scratch paper, I take the square root of the first one, which becomes this. I take the square root of the last one, which is 5, and then I multiply it to myself. So what would be the answer? The answer would be 10x squared plus 5x exactly. And this is exactly what is sitting in the middle. So this means that this is indeed a quadratic rule. So this means the square root of the first one, and then plus the square root of the second one to the 2, but we don't need these squares, these brackets involved, so this becomes x squared plus 5x plus 5 to the 2. Yes? But can I factorize this more? So this is already factorized form. So this is the product of two same terms. Yes? But can I factorize this? You can factorize this, but not on the set of integers. Why? Do I have two integers whose sum is equal to 5 and the product is 5? No. So this is the end of the problem. And then this would be the answer to this problem. Okay, so until the next video, be safe and goodbye.